What you just heard was a 4-part chorale. However, did you know that that chorale there was composed entirely by an artificial intelligence? So here I have some instructions for those who are practically minded in case you want to follow along. You can actually train and build the model that I will be presenting just by following these instructions right here. My talk today will be about BachBot. BachBot's goal is to generate Bach chorales, so 4-part harmonies, in a manner that is indistinguishable from actual Bach to the average human listener. And so today, we're going to start by covering some music theory primer so that we're all on the same page. We'll then talk about how we process musical scores such that they're amenable for processing by recurrent neural networks. After that, we'll discuss the model that Bach used and introduce recurrent neural networks, long and short-term memory, and how we apply these in order to encode and process musical scores. We'll then demonstrate some results showing that recurrent neural networks seem to attenuate to music theoretic features, such as cadences, chords, and fermatos. And finally, we'll release results about the largest musical Turing test to date, spanning over 1,700 participants, where we found that only 5% of responses significantly differed from random guessing. I want to start off by talking about music theory with everyone. And so when I think of music, this is what we're thinking of. We have on the x-axis here, time, and on the y-axis, we have pitch. So a pitch is how high or how low a note is, and notes are held for various durations. Now, what this representation here is called is a piano roll, and we can interpret it as follows. Every bar, when it appears, is when a note is pressed down, and it continues until the bar disappears, at which the note is released. Since we're dealing with 4-part harmonies, at any point in time, there is a maximum of 4 possible bars in a vertical slice. Now, this kind of musical representation may seem unfamiliar or kind of strange. In fact, you're probably used to seeing music that looks like this. Oops. Like this. This is much more normal. This is standard musical notation. And some parts I want to point out here are 4-part chorales, so soprano, alto, tenor, bass, corresponding to the 4 different bar lines. Pitch here is now represented in terms of how high or how low the note is with respect to each of their bar lines. Duration is represented by the flags on the notes. So in this case, the quarter notes have no flags, and you can see this crazy little note right here, which has 3 bars under it. This is actually a 30-second note. One thing that's also important to note here is the presence of fermatos, these little hats right here. So that little hat there, right after the 30-second note, it's a fermata. And what this signifies to the performer is, I want you to hold, and I want you to attenuate, and I want you to hold on this note, and I want you to pause. Fermatas were used by Bach to signify the end of phrases. Phrases are what actually give Bach's chorales a sense of conclusion and a sense of progression over time. So capturing this notion of phrases is critical to generating realistic-sounding chorales. Awesome. That's all the music theory we're going to talk about. Let's move on to the AI. So we start with a corpus of all known Bach chorales provided by the Music 21 dataset. And the first thing we do is we transpose it. So we take all of the scores and we transpose them to C major and A minor. The reason why we do this is because it's not really the absolute pitch of a score that is unique. Rather, it's the differences in pitch that really that really define what a musical piece is. You could sing Happy Birthday at any tone you'd like. It's still Happy Birthday. We also quantize. So notice that the 32nd note, the note that has 3 bars under it, has now become quantized to a 16th note. This is done in order to turn notes into a sequence of frames, which we can then process. If we did not quantize, then you wouldn't be able to process this sequentially using a discrete time recurrent neural network. Here's a question for the reader. Here's a question for the audience. I have 4 parts: the soprano, alto, tenor, and bass. Each of them, in standard MIDI encoding, can play one of 128 different pitches. how many possible frames how many possible frames, so simultaneities with up to 4 voices, can be created? The answer to this is on the order of 128. There's some adjustments. You know, the soprano can't play lower than the alto, but on the order of, it scales 128, number of notes exponentiated to the number of parts. So for high degrees of polyphony, so if you have more than 4 voices, which is very common in modern music, it actually becomes intractable to represent the entire vocabulary of possible chords. So we can't actually use a frame-based representation where we model every sequence or every point in time as an individual token inside of our sequence. How do we deal with this? Well, this problem also arises in text classification. One way you can classify text is by individual words. But another, you could also imagine processing individual characters of words over time. And that's the exact analogy we take. Rather than representing individual frames as like 4 parts simultaneously, we break it down into individual parts by ordering it soprano, then alto, then tenor, then bass, followed by a frame delimiter. So the processing looks like this. We start at the very top note, the soprano note, and we work our way down until we get to the bottom. We then emit this triple bar thing, the frame delimiter, and then we go to the next note. And so the encoded sequence looks as follows. You have a start token, you have the 4 notes, and you have the frame delimiter. But there's one thing I have neglected to mention, and that's how do we represent duration. And so that is actually what you see right there with those Booleans following the note numbers. True means that the note is articulated at this point in time, whereas false means it's actually a continuation from the previous note in the previous time frame. So if we look right here, we see that the trues indicate that this note has been played at this point in time. It is newly articulated. So we do this to every single Bach chorale that we have in our data set, and we arise at a corpus where the vocabulary size is 108. This is not too surprising. It indicates that not all 128 possible pitches were actually utilized after we had transposed things to C major. However, we see that there are about 423,000 tokens in our entire corpus. It's a pretty big size, and it makes us excited because now we can consider more sophisticated models such as recurrent neural networks and deep recurrent neural networks. If you're following along with the Docker demonstration, what I've described here is implemented by the following commands. So transposing, quantizing, and encoding into the sequence happens in this first left part of this sequence diagram with the command BachBot datasets prepare. You then receive these encoded sequences with the .utf extensions, where you call BachBot datasets concatenate corpus. And what that does is it takes all of these encoded scores, puts them into one HDF5 file, which is then used for our training data set. Awesome. We have our encoded corpus. The next step is to model it. To model this, we're going to use a model called a recurrent neural network, which I'm sure you've heard plenty of today, so I'll go kind of quickly through these slides. This is a neuron. It's the fundamental unit of computation inside of a recurrent neural network. It takes a d-dimensional input and then linearly combines them using the weights W. And then it sums them all together to get this activation Z. And then the activation Z is passed through a sigmoidal activation function, sigma, in order to produce the output Y. You can put a bunch of them side by side, and you can start stacking them into layers. And this forms what's known as a feed-forward network, where you have your input layer, which is the tokens, and then there's some sequential units of composed sets of hidden layers, to finally resulting in the output layer. A recurrent neural network takes this idea and adds the notion of memory. So again, we have our input here represented on the bottom left here, but we have this new thing called the memory cell. And what the memory cell is doing is it's taking the hidden layer activations, HT, from the previous time, so that Z minus 1 is a unit delay, and it passes it back in as inputs for the current time. So in effect, this hidden state is being propagated forwards in time, and it acts as a form of memory, allowing us to remember where we are in the composition and helping us to generate more realistic notions of phrasing, conclusions, and conclusions to phrases. I've taken that memory cell and I've put it in this little shaded cell called H. There we go. So I've taken the memory cell and I've compactified it into this H unit right there. And if we stack them together, so we take the hidden units from one layer and we put it into another hidden unit layer, we have this stacked recurrent neural network on the left-hand side. Of course, that looks a little strange. We don't really see Z inverses when we see recurrent neural networks. Instead, we're used to looking at this unrolled format on the right-hand side. So on the right-hand side, what I've shown is the sequence of tokens on the very bottom, the x1 to xn. And on top of it, I've shown the first hidden layers, the second hidden layers, and finally, the outputs of this recurrent neural network. To train this network, we train it to predict the next possible token inside of our sequence of tokens. And this is done using the backpropagation algorithm, where we backpropagate the error signal through gradients up to the network model parameters. And we step the model parameters using stochastic gradient descent to optimize the next note predictions. Of course, what I've described is something that's known as a Jordan-type recurrent neural network. You can have more sophisticated hidden units. And so in this case, the memory cell we actually utilize in BachBot is a long short-term memory. This has been talked about in previous presentations. It is basically the constant error carousel is the Jordan RNN we've looked at previously, but we've added an input gate, a forget gate, and an output gate represented by I, F, and O. If you're following along, the command which actually implements this recurrent neural network and trains it from the concatenated corpus is called BachBot train, and it utilizes torch RNN under the hood. Okay. After you have the trained model, you can then call BachBot sample, and what that will do is that will sample the model, in order to generate novel compositions. And the sampled model is still a sequence of tokens, so you can finally call BachBot decode, and that will take the sequence of tokens and decode it back into music, which you can then listen to. So if you're following along, run this command, and you should be able to produce your own novel compositions. Awesome. So we did exactly what we were described inside of the practical instructions, and here are the results we found. As expected, dropout causes higher loss in training, but lower loss in validation. This is expected because dropout turns off connections at random, essentially forcing the network to learn features which are robust and not codependent on other features. And so we find that the best dropout occurs with 0.3, so a 30% probability of turning off any unit during training. And that's represented by the purple curve, which has the lowest validation loss, but definitely not the lowest training loss. The lowest training loss is actually achieved with 0 dropout. This is a little more interesting. Here I'm showing the activations of the individual neurons as we process a score. Where's my mouse? So this is a little hard to see, but what I'm showing up top here is this is the input to the network, and here are the activations of the network over time. The first layer, the second layer, the third layer, the fully connected layer, and the outputs of the network. Now, there's some obvious patterns. You see these little smears right here. Those correspond to rests or notes that are held at the end of a phrase. And that little smear seems to show up across all of the different layers. But other than that, when I look at these hidden unit activations, I couldn't tell you very much about what's going on. This is a common criticism of deep learning models, that they're black box and not interpretable, but surprisingly produce great results. And indeed, if we look at the very bottom, the outputs of this network, we have here what kind of looks almost like a piano roll. This shouldn't be very surprising. The network was trained to predict the next note predictions given the current note and the current hidden state. So if the network is doing perfectly, you would actually expect to see the input reconstructed but delayed by 1 time unit in this very bottom layer. So somehow, this jumble of noise produces pretty good next note predictions. Here's a slide I find particularly interesting. What I'm showing up top here is an input score represented in piano roll notation. And here I'm showing some neurons and their activation values over time. Now, these neurons actually seem to be learning something about music theory. For example, I believe this is actually a G7 chord that this neuron is very selectively firing on, and this neuron here seems to be doing the same. There's other neurons. There's other neurons being shown. There's other neurons shown here, which are more fully described in our paper. But the conclusion from this slide is that these neurons seem to be adapting to learn music theoretic features without any form of prior supervision. We didn't tell the model about what a cadence is, what a chord is, what a tonic is, yet the model has chosen to learn these sorts of features in order to help itself optimize on an automatic composition task. Finally, we demonstrate that the model is able to compose realistic sounding music by generating some samples from it. So what you heard at the beginning was one sample. You might recognize that song. It's obviously not Bach, but we've still been able to, but this demonstrates the flexibility of our model. By clamping the soprano notes to be those of Twinkle, Twinkle, Little Star, we're actually able to generate a Baroque harmonization of what Twinkle, Twinkle, Little Star might have sounded like if Bach was tasked to harmonize it. Finally, I want to share some results about what happened when we put up BachBot.com, which you're all welcome to go to and test yourself on. It's a musical Turing test where participants are tasked with discriminating between, is this sample real Bach or is this sample generated by BachBot? And so we put this test online. We received about 1,700, actually almost 1,800 as of today, responses. Most of them come from the US and the UK where this research was conducted, but participants span all over the world. Here's a breakdown of participants by their age and their music experience. Something that's interesting to note is that we actually have a surprisingly large number of advanced participants. So advanced is defined as someone who has either formally studied music theory, and an expert is someone who is designed as a professor or teacher of music theory. And we can see that their participant amount is non-trivial. This is not something you would expect if you were to run this study on Amazon mTurk. Here are our results. These notes, this code down here designates the problem type. So S means that BachBot was tasked with harmonizing just the soprano part given the other, or with the soprano part given the other parts. And same with ATB. AT means that the soprano part and the bass part were provided, and BachBot was asked to fill in the intermediate parts, the two in between. And same with ATB. It was just given the soprano part, and it was asked to compose a harmonization. Finally, SATB means BachBot was not clamped to do anything, and it was asked to generate its own compositions. The result that's important that we should all look at is this one right here. What this is showing is that, on average, participants are only able to differentiate Bach from BachBot 7% better than 50%. Now, if I give you a discrimination question with 2 choices and you randomly guessed, you would get 50%. And so what this is showing is that in BachBot, the gap between the two is only amongst 7% of question respondents. Of course, here you see the expected trends if you segment further by music experience. With increasing music experience, you're able to differentiate Bach from BachBot better. Novices, so casual listeners of music, are only able to differentiate Bach from BachBot 3% better than random guessing. And something that I find a little anomalous is this base column right here, where the trend that increasing music experience leads to better discrimination does not hold. For some reason, experts are doing significantly worse than every other participant group. One possible explanation for this is, recall, when we ordered these notes sequentially, we had ordered them soprano, alto, tenor, bass. And so what that means is by the time BachBot is tasked to produce what the bass note might be, it has already seen the soprano, alto, and tenor note for that harmonic context. So it may be easier to generate the bass parts than the other parts. So what can we conclude from this? BachBot is a 3-layered deep LSTM. And what this shows is a deep LSTM model can compose, complete, and generate polyphonic music. By the way, BachBot has also been integrated into Google Magenta, a TensorFlow project that's focusing on generative art. If you look at the polyphonic RNN model in Magenta, it is the BachBot model. The model appears to learn music theoretic notions without any form of prior knowledge or preemption. So we just tasked it to optimize an automatic composition task, and it chose to use this notion of chords and cadences and tonics in order to do well. And finally, we've conducted the largest musical Turing test to date with over 1,700 participants. And our results suggest that the average participant can only differentiate Bach from BachBot 7% better than random guessing. That's the end of my talk. Thank you so much for listening.
Thank you very much for this talk. By the way, my girlfriend studies music, and I'm sure she will like it. My question is, maybe I didn't understand that really, how do you synchronize bass to alto and tenor and so on? Is that, because you were saying each of these was looked at individually. Doesn't even matter how they are composed, or do they have some kind of relation to each other?
So we don't explicitly encode any notion of synchronization between the 4 parts. We kind of crossed our fingers and hoped that after seeing enough data, the LSTM would learn that if the bass note is or if the soprano and alto note are playing these things, then the tenor and bass notes ought to be playing these things. So there's no explicit synchronization mechanism. Rather, the harmony of any frame is really learned from data.
Thank you.
Thanks. Any more questions? Hi, thank you for the presentation. A quick question. When you came up with a 57% success rate, or I don't know how you want to call it, did you take into account the fact that some of the people you ask, they actually know the Bach compositions? So and that's the reason they can actually tell.
Yeah, that is a very valid concern. We did not account for that. That perhaps explains why experts performed much better than novices who are unfamiliar with the corpus. We had actually done a follow-up, or we actually segmented the responses and their discrimination percentages by question type. And when we had a music theorist look at it, they found that people were differentiating well-known Bach chorales better than the more obscure Bach chorales. So that is a valid concern. We didn't address it in the aggregate statistics reported.
Thank you. Any more questions?
Such a short question. I hate to have you walk the mic over. I wanted to know, you've obviously built BachBot. Do you have plans for building other musician bots or impersonators?
I don't personally have plans. I know that, so Magenta has implemented BachBot as their polyphonic RNN model, and they actually have a variety of corpuses that they provide. So they have one for like 8-bit game music. So if you were interested in training the BachBot model on any of these polyphonic data sets, I'm sure Magenta has provided really great frameworks for doing so.
Any other questions? We have time probably for one more. So one last question. Hi. What's the
the input to the model, do you require it to be already transcripted? So are you processing MIDI files, or is there a step, to transcribe audio or take regular music notation and turn that into those blocks?
So we decoupled the actual transcription of music into the generative modeling of it. So we assume as input MIDI, music XML, pre-transcribed music that we can already run software packages on.
Thank you very much.